But I'm very happy to actually give the talk here and not downstairs because, I feel less the pressure that you may fall asleep. Here is a nice couch. You can just sleep if you don't like the talk. I'll try to do my best to make it lively, but not so. Most of the things that you're going to know, they somehow will resonate with what you have seen on the first talk this morning. So I'll try to. So I changed about a little bit the flavor of the talk after your presentation this morning. I hope I'm not gonna mess up everything. So the talk is definitely about collective brain dynamics, but as you know, collective can be anything. So it can be the co-activation of a small ensemble of neurons for whatever reason, but that could also be the synchronization of a large population of neurons across different areas. However, the very motivation for this talk comes from the coexistence of two collective behaviors. On the one side, oscillations, on the other side, neural avalanches. I'm pretty sure you're all familiar with oscillations, and from this morning, you're also familiar with neuronal avalanches. Now, here I'm showing you an example of alpha oscillations in the resting state of the human brain. You can record alpha oscillations using MEG or EEG on scalp, so not non-invasively. So as you know, alpha oscillations, as all the oscillations, by definition, they have a characteristic time. And to some extent, they also have a characteristic amplitude. That means that overall oscillations, they do have characteristic scales. So I will call oscillations a scale-specific phenomenon. Now, on the other hand, avalanches are not scale-specific. They are scale-free, which means they do not have a characteristic scale. Now, this morning you have seen avalanches in single neurons, in fMRI, in a different system. Here I'm showing you an example of avalanches recorded on the MEG of the human brain, resting state. So this is an avalanche, and each of the dots that you see here, they simply represent excursions above thresholds in a given sensor. Okay, so this is an avalanche across a collection of sensors. All right. Now, if you just count the number of dots that you see within the avalanche, that is going to be the size of the avalanche. And then if you plot the distribution, as you know from this morning, this distribution is a nice power law. The power law simply means that you do not have a characteristic scale for the size of the avalanches. So the dynamics has no characteristic scale. Now, together with this power law, you have other scaling relationship and scaling features for the avalanches. I'm not showing them here. Altogether, this points to criticality. At least those are signatures of criticality. I put there a question mark because this is not proving that actually we are at criticality. And also because most of the modeling attempts that have been done to reproduce neuronal avalanches come from the statistical physics point of view, which is trying to answer the question whether criticality in the brain is self-organized or there is some sort of tuning. Okay? So now this is a very horrible slide, very dense. I don't want to talk about this slide. This is just to say that I'm listing here a number of attempts, modeling attempts that have been done, so that are now, pretty much standard in statistical physics for avalanches. Using nice power laws, you realize there is no oscillations here, because in most of these models, there is no trace of oscillation. Especially in self-organized criticality, you cannot have oscillations, except if you decide to put by hand oscillations in the system. Now, you may be more familiar with the simulations, with modeling of oscillations. In this case, I'm also showing here quickly just 3 potential scenarios. We have more complicated modeling strategies for oscillations. They are more accurate, and the questions that you ask are typically different. So you want to know the biophysical mechanisms which are behind the emergence of a given type of oscillations in a given area of the brain. You want to know what are the control parameters for those oscillations oscillations, and so on and so forth. And finally, I mean, sometimes you ask what is the dynamical regime. The brain needs to be tuned in order to have oscillations. Now, what are we after here? So what we want here is a minimal physics model that is analytically tractable. Not all models that we have seen are. Most of them, they are actually not. And at the same time can capture the coexistence of avalanches and oscillations in a quantitative way. So we want also a model that is able to tell us something about the characteristics of the coexistence regime. And hopefully, our model will give us some testable universal predictions that then we can verify in experiments. All right, so now he did a much better job. This is a terrible slide to introduce the Ising model. Sorry, sometimes I will say Ising model because in US is the Ising model. In Europe, correctly, is the Ising model. But sometimes I'm used to say Ising, so I apologize in advance. So in the Ising model, you know, so we have this structure. So that could be spins. Originally, they were spins. Could be neurons. I would say a collection of binary variables. This is the Hamiltonian, which is governing the dynamics of this system. Now, in the case of the interaction is ferromagnetic, that is, you only have excitation, right? And without external field, so H is equal to 0, then you have a phase transition. That is, you have a transition from order to disorder at some given temperature, Tc. I will call this state criticality, and you have at criticality, you have all the beautiful properties you have seen this morning. You have scale invariance. That is, if you zoom in and out, this will look always the same. If you measure the statistics of those clusters here, it's a beautiful power law with an exponent around 2. And all the dynamics, basically, they're all described by power laws. That's nice, but if you look for oscillations, forget it. Here, you cannot have oscillations. So in the Ising model, at equilibrium, this is a model of equilibrium, you do not have oscillations, okay? So what can we do with this model then? Well, we start from the simple model and we just do a little addition. So we add a negative feedback, which is proportional to the global activity of the system. The global activity is defined as M, as you see there, okay? So now, each neuron is feeling the the interaction with the nearest neighbors, or with, depending on the connectivity, okay, but it's also feeling a negative feedback, which is proportional to the activity of, in this case, in this picture, of the entire system, sorry. So in short, you have your stochastic dynamics. So this is the equation you have seen before. Now there is an external drive, which is not external actually, because it's given by the internal activity. Okay, this is your Monte Carlo dynamics. You do whatever. It can be Glauber, can be anything. Okay, plus there is a deterministic part, which is the equation for the feedback. Okay, now you can think of the feedback as an adaptation strategy. Can be spike threshold adaptation, for instance, if you want. And as you change or inhibition, because you can also change the pooling, you can also have a local feedback, more local feedback. So you can go from something that is global to something that is more local to the limit of self-feedback. So the spin is also only feeling its own field, okay? Now, in the fully connected continuous time limit, which is the mean field behavior, we can solve the model analytically. I have to run because I'm already getting late. So we can solve this model, okay? So the model is equivalent to a system of Langevin equations. We can linearize the equation around the stationary point, which is m equals 0, h equals 0. Now, without feedback, this is exactly the Ising model. So you get a second order phase transition at beta equal 1. But when we have a feedback, that's the equation you get, which is nothing but a van der Pol oscillator. Now the second order phase transition becomes a Hopf bifurcation at beta equal 1. So because of the feedback, you are out of equilibrium now. Remember, this is important. You are out of equilibrium and you have a dynamical transition to oscillations, okay? Now, Again, in linear approximation, I know the solution of this equation. I can draw my phase diagram very nicely. There's a region that I don't care about, in which I have simply Ornstein and Uhlenbeck process, no oscillations, because I have two real eigenvalues. Then when I cross the red line here, I get two imaginary eigenvalues. I get oscillations, intermittent oscillations. They become more and more prominent as I approach the critical point, which is beta equal 1. Then when I cross the critical point, I get an oscillator, a simple oscillator. Okay? Okay, let's take some break with a simulation. This is a 2D connectivity. Okay? So the model is basically random when beta is far from the critical point. So when we approach the critical point, you see some fluctuations, but you start to see some like pulses. And when I get to the critical point, you definitely see like nice pulses plus these islets as before. And when you cross the critical point, you have what we call harmonic oscillations. Okay, now that's all beautiful. I like it, but we need to match that with data to see if actually this model is good to reproduce oscillations and avalanches in the data. So we take MEG recordings of the resting state of the human brain, 14 subjects, 273 gradiometers. We know we have an analytical form for the autocorrelation of the activity. Okay. Now we can simply get the parameters beta and C of our model by fitting the analytical autocorrelation to the empirical autocorrelation of each sensor. Here is an example. The fit is pretty good. We do this for all sensors and for all subjects. We draw a distribution, and you see that the model wants to be very close to the critical point, but slightly below. So this peak is around 0.99. Okay. What we do from now on, we simulate the model at beta equals 0.99, and for C we take 0.01. C is just getting the main the frequency of the oscillations, the dominant oscillations, which is alpha in this case. Okay. All right. So let's see what we can do with oscillations. I mean, that's the simulation versus the MEG. They're pretty nice. I mean, qualitative match. It's good. We want to quantify that a bit better. So in order to do that, one can take the area under the signal, okay, and take the distribution, okay. So as you see, we are pretty close to the data. So we have one simulation versus like 14 subjects, okay. The functional form is exactly the same. It's approximately Weibull, approximately. And as you see, this is independent of the threshold that we take, okay. So getting the parameters from the data, we get a good match, quantitative match between model and data. But we can do something more. So as you know, I mean, like fluctuations, also especially in neuroscience, the correlation properties of the amplitude fluctuations are pretty important in MEG and also in EEG signals, and they're usually studied using the trended fluctuation analysis, okay? So I'm not going into details, but what you do with DFA, you estimate the scaling of the fluctuation function. That is, you get this exponent here. Now, if this exponent is larger than 0.5 and approaches 1, between 0.5 and 1, you have positive long-range correlations, okay? So what our model is saying about the trended fluctuation analysis is that actually when the parameter that you fit from the data, you get from the data, the beta that you get from the fit with the data gets closer to criticality, that is closer to 1, also alpha, the exponent of the DFA gets closer to 1. Another important prediction is that closeness to criticality correlates with the total power that you have in the alpha band. So the more power you have in the alpha band, the closer you are to criticality. Okay, so this is about oscillations. Now I have to show you that actually you can reproduce collective dynamics. Now, in order to do that, I need to map the sensor array from the brain to the model. So I can do something very simple here. So I can make subsystems in my model, and then the signal that comes from each subsystem is going to correspond to one sensor, okay? Once I've done that, I use the same strategy to analyze the data from the MEG and the data from my model. So the first thing I have to do, as I showed you before, I have to get these peaks over threshold, okay? So for instance, I do that in the data. I go from 273 continuous signals to something that looks like a raster plot, okay? In the raster plot, I can identify the avalanches as these continuous stripes of activity, measure the sizes, and then compare the distribution in data and model. So as you see, we are very good at Riemann. And besides reproducing the distribution of avalanches, we also reproduce the scaling relationship between the sizes and the durations. Okay, I could show something more about this, but I changed a bit my program. And so what is important to say here is the following. So as soon as you move, so 0.99 is slightly subcritical, very close to criticality. But as soon as you move already to 0.95, the power law fit is actually failing. So you don't get the power law anymore. So it looks like the model is telling us that the system actually seems to be very close to the critical point. Now, if this is actually true, if the system is close to the critical point, then if I look at the system, if I zoom in and out, okay, then I should see always the same picture statistically. So what I call this statistical similarity. Okay, so you expect to see that the picture, let's say some probability distribution, some scaling law is preserved when you zoom out or in, for instance. Okay, now if you have a good coarse graining strategy, you can actually test this prediction in the data, and then we will see what we get in the model. Okay, because in the model we have a critical point. Okay, now the strategy is the same strategy you have seen this morning. Okay? But just I'm applying the strategy to MEG data. Okay. Now what I'm doing, I'm pairing the sensors according to their pairwise correlations. So I'm ranking them from the most correlated to the least correlated, and then I pair them. Okay. So on the first step, I go from n to n. I reduce the number of variables by half. Each time I apply this procedure, I reduce by half the number of variables until I'm left with just one variable, let's say, and I cannot do anything. Okay, so this morning you have seen some quantities. I decided to focus to some, okay, some of them are the same, some others are slightly different, okay? But I mean, like, because I think that's closer to the way neuroscientists are looking at data. So probability of activity, that's one quantity you can look at, okay? We expect this probability to, when we coarse grain, to get to get towards a universal form, which is also non-Gaussian because we have no local interactions here. So we do expect in the brain not to have local interactions, okay? Not only local interactions. The probability of silence, you have seen that this morning, but just you have seen the free energy version, so the minus log that expression that then scales as k to the power of beta. I'm showing you that this probability is just a stretched exponential. Basically, it's not exponential because if that would be exponential, that would be trivial. So it's important that this probability is not exponential, or at least we think it's not going to be exponential. And then the autocorrelation time. Remember, we have long-range correlations. So the DFA told us that we have long-range correlations. Okay, so then when I coarse grain, I'm left only with the slow modes. That means that the autocorrelation time has to grow when the cluster size of the coarse graining is growing. Okay, and finally, you have seen this morning, which is the eigenvalue spectra of the covariance matrix. I'm adding something there. If actually we are criticality, we do expect that the avalanche properties, they should not change, okay? Because these are part of the dynamics. So the dynamics has to be always the same, okay? All right, so I'm about to finish. So that's the picture, the overall picture. Everything looks pretty much as expected. You see that the probability of activity is converging towards a fixed point, a fixed distribution, which is not Gaussian. The probability of silence is scaling as expected. The autocorrelation time is scaling as expected, plus the eigenvalues, the eigenvalue spectrum of the covariance matrix is scaling as expected. The avalanche size distribution and duration do not change. The scaling part here is not changing. This is finite size effect. So because when you coarse grain, you have less and less variables, and then of course the maximum size is decreasing as expected. But please notice as the durations, they do not change at all. When you do this coarse graining, if you had an avalanche before, you're going to have the same avalanche with the same duration, just the size is going to decrease. The avalanche is going to stay there. This is a big argument to say that actually this coarse graining procedure is not changing the dynamics at all. Now, from the modeling point of view, not so good news. We got something well, or kind of well, with a globe. Let's say this is like the mean field model, so very simple. It's already too much that we get the probability of activity, the probability of silence, the scaling in the silence, but the scaling in the autocorrelation time is clearly wrong, the exponent at least, and we for sure don't get the scaling here. Right? So we thought this is because it's mean field. That's the problem with mean field. Let's go to 2D connectivity, which is the opposite extreme, in which you have only local connectivity. Things look much better. The probability of activity is not a super nice match, but it's not that bad. It's like, it looks like it's not Gaussian, at least when you increase the for large case. But the avalanches, they are also good, but I think this is a spoiler. I think what the model is really telling us is that to match the exponents, we need somehow to take into account the underlying topology. So we are at critical, I mean, this model has a critical point. We are at criticality. So we tune the model to be at criticality, but still we cannot match the numbers, the exponents, and also somehow the shape of that distribution, which is actually expected not to be Gaussian because of non-locality. And perhaps we need to interpolate between the overall fully connected connectivity and 2D, something more realistic, which could be actually the connectome. We did not try with the connectome, but could also be a small world network. I don't know. So with this, I thank you, and I apologize again for the delay. I would like to thank my collaborators, and also to advertise this very nice workshop that we are organizing in Venice in June, July, end of June, beginning of July. The abstract submission deadline is May 15. Please apply. We have a nice set of invited speakers, so you find all the information you need here. And thank you again.